the main thing introduced last time was functions with different numbers of input variables. So we traditionally first learn about functions of one variable, for example, f of x equals x squared plus 1. And in order to graph, there's one input dimension, one output dimension, total of 2 dimensions needed. So this is why a sheet of paper, which is naturally two-dimensional in nature, because it's sort of infinitely flat, almost. Anyway, that you sort of write on paper as if it's two-dimensional. That works to graph something like this parabola, right? So the thing is, one dimension lower, if you don't need to draw the output on its own dimension, but instead you just draw what are all the inputs leading to one output, that's the level set, you only need one dimensional space for that drawing. You have functions of two variables, for example, f of x comma y equals x squared minus 3xy plus 1, and the dimensions needed to graph this, 2 plus 1. You need 3 dimensions total because there's two input variables, so two axes are used for input, and then z, I guess here is output, is the output variable, and that's going to be another dimension, so a total of 3. But if three-dimensional drawing is tough, then at least if you just look at what's going on for one specific output and ask which combinations of inputs lead to that, you can draw that in two-dimensional space. Then you have functions of three variables. For example, f of x comma y comma z equals x, y, z minus x over y plus z plus 8. And if you need to graph this, the graph is going to require four-dimensional graph paper. Three input dimensions, three axes for the inputs x, y, and z, and then you need a fourth dimension, one more dimension necessary for the output. That's four-dimensional. That's now really tough, and so this gives a good reason why we were looking at level sets earlier. At least for the level set of something like this, you fix a specific output, and you ask which combinations of x, y, z, which triples, would achieve a certain output, and that's going to be a three-dimensional picture. Now that picture can still be tough to draw because it's three-dimensional, but imagine trying to draw the graph, which is four-dimensional. Okay, I'd like to review limits from Calc 1. So here's the graph of f of x equals sine of x over x. So it looks like the graph of sine of x, except when x gets big, you're dividing by a large number, so that's why this is going to kind of shrink out. And then when x gets small, the effect is not too much, except this key issue of when you actually use x equals 0, well, then you're dividing by 0. That's why there's this hole right where the y-axis is. You'll note that for this function, the limit of the function as x approaches 0 is 1, since the limit coming from the left and the limit coming from the right are both equal to 1. And recall that for a limit of a function of this kind, as x approaches a certain x value here called 0, recall that for a limit to exist, the limits from both directions must be the same. I mean, we only have two one-sided limits, right? From the left and from the right. But the limits from both directions have to be the same. So take a look at this example. The function here is g of x equals absolute value of x over x. And the limit doesn't exist because the limit from the left is -1 and the limit from the right is +1. So again, recall that for the limit to exist, the limits from both directions must be the same. And here they're different. We got a -1 and we have a +1. Okay, the official definition, though, looks something like this. There are a lot of details here. We don't need to maybe dig into all the details in too careful detail, but if you've taken a class on mathematical proof, maybe you'll appreciate some of what's being said here. So first of all, the function f has a limit L as x approaches a, and we write this notation if, and then here's the kind of language that's very proofy, but it looks like this: for all epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than absolute value of x minus a is less than delta, then absolute value of f of x minus L is less than epsilon. Okay, just note here that x minus a absolute valued is the distance between x and a. And you can say a similar thing about the distance between f of x and L. There is a concept of limit for functions of two variables. And look at how similar it really is. So the function f has limit L as xy approaches ab. And we write the limit of f of x comma y as x comma y approaches a comma b equals L if, and then I hope this looks fairly similar, right? So if for all epsilon greater than 0, there exists delta greater than 0, such that if that much looks the same. 0 less than, that's the same. Earlier we had absolute value of x minus a, and we had just commented that that's the distance between x and a. Now we have 2 points in two-dimensional space, right? So there's x comma y, there's a comma b, and so here, without actually invoking the distance formula, we're just saying the distance between the points x comma y and a comma b. So that's meant to look like the absolute value of x minus a earlier, since that is a one-dimensional nice version of what the distance is. Okay, less than delta. Then absolute value of f of x comma y minus L is less than epsilon. This is a lot to dig into. Please maybe don't overstress about the way this is all worded. We're not going to do this in the form of a very complete proof or anything like that, but it's just worth seeing once. In Calc 1, just remember the thing that we already saw by example and non-example, that the limit exists if both directional limits exist and are equal, right? The limit from the left and the limit from the right, if they exist and are equal, then the overall limit, the two-sided limit as we often call it, exists. Now I'm using this word both because I want to kind of extend the language a bit and say here what's really happening is that the limit exists if the limit in all directions exists. Okay, and they're all equal. So all directions, well, there's only two directions. You know, if you have x approaches a, you can either approach from the left or from the right. But then the point is, in what we're about to look at, there's more than two directions. So for example, let's look at f of x comma y equals sine of x squared plus y squared over x squared plus y squared. Here's a contour map. I'm not expecting you to exactly know what the graph of this looks like. We are actually taking sort of the earlier picture and doing sort of a two-dimensional version of this. You'll see here all the points where the output is 0.6 forms a circle, and all the points where the output is 0.7, all the xy's where that happens, forms its own circle that's of smaller radius. And as on and on it goes, all the points where the output is 0.95, from those points on the xy plane form a tiny circle centered around the origin. And the thing is, no matter which way you approach the origin, you can see by these level sets with output 0.6 and 0.7 and 0.8, 0.9 and 0.95 that the z value, the output, keeps approaching 1, no matter which way you head in. So because of that, our conclusion here is that the limit of this function f of x comma y as x comma y approaches the origin is equal to 1. Looking at another example, this is the function g of x comma y equals x squared minus y squared over x squared plus y squared. Now, if you were to graph level sets here, all the points where the output is 1, that happens to be all along the x-axis. And I don't know if I can convince you that there aren't other points somewhere else that should be in blue or not, but I can at least convince you that all the points that are shown in blue should have output 1, because all along this line, the x-axis, the y-coordinate is 0. So look up here, it's x squared minus 0 squared, in other words, x squared. The denominator is also x squared plus 0 squared, in other words, x squared. So you really, all along this line, have x squared over x squared, which simplifies to 1, right? The only exception is when x equals 0. There should technically be a hole right at the origin. Okay, and then all the points shown on this line through the origin with a slight positive slope, that's where the output is negative 0.5. This line where the slope is, I believe, 1, and then also this other line where the slope is negative 1, those are all the points where the output is equal to 0, and on it goes. But here the point is, okay, this picture is a little approximate. You can see what this really looks like using Desmos, and we'll do this in just a moment. But the key point is that traveling along different straight paths to the origin, the z value approaches different numbers. In fact, if you follow the yellow line, one of the yellow lines all the way to the origin, the output's always 0. And if you follow the orange line towards the origin in a straight path, then the z value is always 0.7. So traveling on different paths gives you different limits. Therefore, we conclude that the limit of g of x comma y as xy approaches 0, 0 does not exist. Let's click on this link and just have the computer in Desmos. Let's take a look at what some of the level sets look like. So here we're seeing we've really just done this very not fancy at all, right? We're really just asking the computer graph all the points in the xy plane where x squared minus y squared over x squared plus y squared is equal to k, and then k is currently set to be 0.5. So it happens to be these two lines. And if we set k to be, let's see, 1, we will see uh, okay, so it should be the the x-axis, but the computer's having a little trouble with that. And then we can, let's say, set k equal to -1. Oh, the computer did fine with graphing that. Well, whatever. Okay. Anyway, the point is, I wish I could click on a point to show, but right now we've got -0.94, right? So when x is 1 and y is like 5.7, I guess, then the output should be -0.94. But then there's another point over here, where x is like zero point 0.5 and I guess y is maybe 2.8 or so. Then again, the output is -0.4. Okay, that's the end of this part.